Hi everyone, today I will derive the Black-Scholes equation starting from no-arbitrage principles, and I will also tell what assumptions break down in practice. So, so first of all, let's go to step 1. So the step 1 is that we will derive the stock price process. So basically first we will assume that our stock price follows a Brownian motion. So its equation become something like this. So dst is equal to mu st dt plus sigma st d of wt. And so as you can see, the equation has basically two parts. The one is the mu st dt part, and that is basically the predictable drift, and the second part is the dwt part. It is basically the Brownian motion part. And in this equation, the mu is the expected return, and the sigma is volatility, and due to Brownian motion, binary process for that. So when we move to step two, the step two is basically now we'll find the option value process. Uh, so how the option value v changes, since v depends upon both stock price s and time t, we use O lemma. So it's basically dv, which is equal to partial derivative v with respect to t plus half sigma square s square del partial derivative v derivative s square plus mu of s partial derivative v partial derivative of s, and this whole comes to dt plus sigma s derivative of v and partial derivative of s dwt. Now why we use it? So it's basically O lemma. It's a chain rule of stochastic calculus, and we need, because v of s comma t is a function of random process s, the extra second derivative term appears because of the quality variation of Brownian motion, and that is why it what makes stochastic calculus different from regular calculus part. And the first part dt is a deterministic part, and the second part ddt is basically random part. So now we'll jump to step 3. The step 3 is basically the portfolio construction part. So the key insight here is, let's create a portfolio with one option and the short delta shares of the stock. So the basically let's call it the portfolio pi is equal to v minus del s. So this is basically a hedge portfolio, and by shorting delta shares, we are trying to offset the risk that from holding the option, and the change of the portfolio d pi is equal to dv minus del d of s. Okay, so uh, if we now substitute this in an equation, so like dv was being derived in step, dv was is that we have done in step 2, and ds we have written in step 1. So when we put these values in this step 3 equation, we get something like this: d pi is equal to v partial derivative v with respect to t plus half sigma square s square del square v and del t del s square plus mu s del v by del s dt plus sigma s del v by del s dwt minus of delta s dt plus sigma s d of wt. So now notice both terms have the same random component, that sigma SDWT. This is crucial, and if we can make this cancel out, we eliminate all risk from portfolio. So let's try to cancel out this. So let's move to step 4. So step 4 basically becomes something like, to make this portfolio risk free, we eliminate all randomness by setting the DWT coefficients equal. So it basically becomes something like this, like we are equating these both. We are setting this and we are equating these, okay, to make the portfolio risk free. So something becomes something like this: S del V and del S equal to delta of sigma S, partial derivative of V. So the SS cancel out. So basically the hedge ratio, that's delta, it becomes something like this: partial derivative of V, partial derivative to S. Okay, so we will substitute this back into our previous equation. uh, that was in step 3. So it becomes something like this: del S. So as you can see, I will change one color. As you can see, so this term del V del S mu S dt. So this terms get cancel out with this term, and sigma S dWt. This term gets cancelled out with this term, and then with this choice, our portfolio becomes something like of this. So I write here, add portfolio d pi becomes something like of partial derivative of V with respect to partial derivative of t plus half sigma square S square, double partial derivative of S square dt. So the portfolio is now completely deterministic and no random terms are left. So we have created basically a risk-free investment. And now let's move to step 5. So the step 5 is basically, we have to apply the no arbitrage conditions. Since our portfolio has no risk, it must earn a risk-free rate. Otherwise, we could make free money. So like then the portfolio value d pi will be equal to r pi dt, where r then pi v minus del s dt. So uh, this is no arbitrage principle. If our risk-free portfolio earned more than the risk-free rate, everyone would buy it and drive the price up. If we earn less, everyone would sell it. The only stable equilibrium is when it earns exactly the risk-free rate. So we're substituting our hedge ratio inside it. It basically becomes r v minus del v, partial derivative of v, partial derivative of s, dt, s dt. And now we can see that we have, basically coming to a step number 6, we have two d pi equations, like one from step 4 and the other one from step 5. So we will equate them both. So it will basically become something like this: partial derivative of v, partial derivative of t plus half sigma square s square, double partial derivative of v to partial s is equal to v minus s partial derivative of v to s. So becomes something like this, and partial s. It has become, we have basically two different equations and we have equated them for the same thing. So that's how our risk-free portfolio changes. They must be equal. And the equality gives a relation that v must satisfy. So by rearranging this, and we finally got our Black-Scholes partial differential equation. I am writing it here at fine clean way. Basically writing here. So the final Black-Scholes PDE equation becomes something like this: partial of v, partial of s, half sigma square s square, double partial of v to partial of s square plus r partial of v on partial of s minus rv is equal to 0. So this is the Black-Scholes partial differential equation. So that's it. So There was the main question, and I have not derived the Black-Scholes equation. There is further derivation from here, which I will cover in the next further videos. So now let's cover the second part of the question, that was what assumptions break down in practice. So the assumptions which break down in practice are basically something these. The key assumptions that break down are the constant volatility part. In real world, the volatility is not always constant, and it's always changing. And the continuous trading part, like continuous hedging part, sometimes like during crisis you are not able to hedge your portfolio, and transaction cost we are not considering, that's also key aspect for this. And like we're considering a geometric Brownian motion, real returns have fat tails and jumps, like in 1987 crash, that was 20 standard deviation of a event, so which was impossible under this model. And constant interest rate, it keeps on changing. And perfect liquidity, sometimes during market stress liquidity dries up exactly when you need to hedge, bid ask spread widen and volume disappear. So despite this limitation, Black-Scholes remain fundamental because it gives the right framework for thinking about hedging and no-arbitrage, and modern traders use it as a starting point, then adjust for real-world complexities with more sophisticated models like stochastic volatility or jump diffusion models. So, thank you.